Okay, I just created two files. The second one will contain all the scripting that we are going to code, and the first one will be, let's call it some sort of main, but the HTML page. So I will go quite quick on the HTML5 part, because I think that you probably are more skilled than me in things like that. So we're just creating a basic HTML page. The two main parts are the head which we need to specify that we use some scripting, and the body. Okay. The head for now is pretty useless, but we can put a title if we want to. I add some style to the body just to show you the difference between the canvas and the whole web page part. And inside of the body we put the canvas part. We have to give an ID to the canvas. Let's call it my canvas, for example. We want to specify a width. You can use or not the quotes, it's the same. And we change the style. And that's the result. I don't know if you are used to Google Chrome, but if you press Shift, Ctrl and A, you see a sort of console which can be useful for debugging purposes, even if debugging JavaScript is not easy at all. Usually it gives you the wrong error messages, and it's quite difficult to reach the real error. But as you can see, we have two different areas. The first one is the canvas, which is white, and the second one is just the border. It's an area we don't care about. The rest of the browser page. If we return here, we want to use some script. So in the end we have the script tag, which have a property, the source, and we put as a source the JS file or any file name if you want to use other file names. And in the body we exploit another function, which is the onload event, which we call the main. Don't forget the semicolon. We exploit the onload event to call a function inside our script file. If we try to execute things right now, we should get an error. Of course, main is not defined because we haven't defined any main, but the file is there. So let's create a function. Let's call it main. This is just one of the many ways in which you can program using JavaScript. If you want to use your own preferred ways, you are more than welcome. And now we create the two objects that we need. The first one is the canvas. Since in index we called the canvas my canvas, I can call using this function here. And then we can create the context. And we call the basic 2D context. Okay. It seems that it works up to here. No errors, so we can presume that we get a canvas and then a context. So let's try to draw something. Let's, for example, try to draw a grid. The grid must have some lines vertical and some lines which are horizontal. So we just create a for loop. I'm using a syntax which is more similar to that of other languages like C, C#. Of course, in JavaScript you can use other syntaxes for achieving the same results, but it's just one of the way. So we call the context. We said that this context exposes some API, so let's use those APIs. First one is move to. Let's move the cursor to some point, and then after moving it, let's draw some line. Which means that I move it to some x values and I draw lines for all the height of my window. I want to do the same for the other direction. So let's create a y variable. In this case, okay. Things are opposite. Okay. If I now try to execute this code, I'm not going to see anything, simply because, as I told you, we are working with a state machine, and there is no state up to now associated to the stroke, the colors, and other values that are required in order to draw. We need to specify which color we want the lines, and only after that we are going to see something. So we set a stroke style, which is basically color. There are different color coding. This one is the quickest and the easiest. And then I call the command to do that. So we see something like that. I don't know if you see something. Let me see. Okay. You just have seen what I meant when I say that debugging in JavaScript can be very, very tricky. I simply forgot here in this declaration to change the X to a Y, and the code simply ignored the thing without giving me any errors about that. So sometimes it can be quite tricky. Okay, let's continue to add some other thing. Let's say that we want to put some axis more. So let's use that other command that is context. Let's clear everything we know about path right now. And that's what you can see. Now if we go more in zoom, you can see that since in this case I didn't care about giving the 0.5 specification to lines, even if I didn't change anything about the width of a line, in this case, since I used the edge and not the half a pixel value, the line happens to be 2 pixels wide instead of 1 as the rect, the grid. Let's do also the other one. this is just to show how it's not so practical to draw in this way, even if it is possible and you can achieve even not trivial results. It can be quite long. It takes quite a time. So I just want you to add one little thing to show how the arc function works, since we are going to use it further on. And without I will put this exercise, all of these things online, so you can look at the code if you're interested too. But let's say that I want to use I want to create a circle without using the arc function. I have to resort to some basic trigonometric function. So let's create a variable that holds all the segments that are going to compose our circle. Let's say that we need a radius, which is going to be 100 pixel large, and two variables for the center of this circle. There are some interesting differences in writing the code in this context and what we are going to do with WebGL, but with the same lines of code. Okay, we put the cursor at the center of the circle, not at the center, at one of the points along the circle itself. Yeah, thanks. We also impose some width to this line. In this case, we ask for just 1 pixel wide line. We can again call those two commands. Let's see what happens. Okay, we draw a circle. Of course, it's pretty blocky, but if we change, let's say 32 segments, it becomes more defined. With 64 segments, it should look like a perfect circle without any differences. Okay, this case study is just to show what happens if we try to do the same using OpenGL, and we will see that it's going to be quite different. But the interesting thing is, if you are able to draw this circle using WebGL, then you know basically anything you need to draw much more complex element, much more complex object. Let's say that there is it's not a curve of learning, it's a wall. At the beginning you face a wall, but then more or less things remains basically the same. It's the beginning which can be a little bit hard. So let's return to the slides. And let's talk about this experimental WebGL or WebGL context. In this case, the canvas element that is exposed will give us the API of OpenGL. Everything about this was already covered. We now have a very different coordinate system and a very different set of geometric primitives to draw. Of course, we also have some different modes for drawing, which will be covered in future lessons. So, even if the monitor, of course, doesn't change, in this case, the canvas and the context have a pretty different set of coordinates, which are centered at the center, of course, of the canvas, and then follows the regular Cartesian orientation. In this case, we don't have any longer pixels as units. Instead, we have floating points numbers with a range that goes -1 to 1. They are called the normalized coordinates. Of course, it is possible to express the coordinates of our object in a range which is arbitrary, and then transform everything inside, normalize it inside this range. This will involve some matricial computation, which will be covered first in the theoretical part and then see in practice. In WebGL, the primitives are pretty much different. In this case, we just have a collection of vertices and we can decide how to hook them together. So, basically, we have 1, 2, or 3-dimensional object that can be drawn using points, lines, or triangles. Anything. All that WebGL can do is basically this. It can visualize a set of points, a set of lines, and triangles, apply them colors and texture, and that's it. All the rest is up to you and the client code. These are the enumerants that specify how we want to use the vertices that we feed OpenGL. We want to use them as points, as lines, line strip, etc., etc. I will show you here what they mean. In the first case, I just specified 5 vertices and I ask WebGL to draw them as points, and so I see 5 points on the screen. In the second case, instead, I have 6 vertices and I ask them to use the lines. This means that each pair of vertices will be connected by a line whose pixels are interpolated between the values of the 2 vertices. If instead I ask for a line strip, then each vertex, except the first one, will be connected to the previous one by a line. So I can obtain, in this case, more lines given a set of vertices. In the first case, I express 6 vertices to obtain just 3 lines. With the line strip, I obtain more lines by simply stating 5 vertices. Line loop closes this range. Something quite similar can be done also using triangles. In the first case, I define 6 vertices. Each group of 3 vertices is used to create the triangles. In the second case, the new vertex, after the first 2 vertices, the new vertex is connected with the previous 2 to create new triangles, while for a triangle fan, there is one vertex that is shared by all the triangles. This can be sound strange for now because probably not all of you have a knowledge about how 3D modeling works. But since there are a lot of ways for modeling and a lot of performance issues depending on what your application have to do, you will see that expressing the fewest possible number of vertices will reduce the number of overall operation that must be performed by the graphic adapter before visualizing something. That's why it's better to have the fewest number of vertices, which become the fewest number of polygons to be drawn. That's why low poly models exist in gaming. The version of a very detailed model can be simplified in order to have a simpler version, meaning with a lot less vertices, and you use textures to hide this difference and still have something that is appealing visually. This is because if you have a real-time first-person shooter, you need a lot of speed, a lot of a very high frame rate to keep the realism of what you are and the engagement of what you are seeing. Okay, we said that with the WebGL you can draw very complex things. For drawing such complex object and to have this high degree of flexibility, the operation that you have to perform are not as simple as those. The problem with the code we just wrote was about it was boring and it was long, but it was easy to understand and to code. In this case, but of course you can only produce very basic pictures. If you want to do something more complicated, okay, you have to pay an extra cost. You don't have at your disposal a list of fixed polygonal drawing function. Mind that in the full OpenGL version there is a mode which is called immediate mode that is deprecated, but you can have some basic object if you want to have them, but in production this is never used. Why you don't have a list of fixed polygonal primitives? Because to draw anything, simply there are too many of them to include all the possible objects that you want to draw. So what you do is to have data that are connected to vertices. You feed those data, you stream those data to the server-side part of the application, and at that point, when all the data you have about the vertices and how you want to draw those vertices is on the GPU, you can call the draw command and the GPU does the magic. The first thing you have to do for passing vertex data to WebGL is to create some. This is one of the ways in which you can do that, but this is the most professional one. You create vertex buffer object, VBO as they are called. If you search online for some tutorial, you know that you can find this keyword, and they will hold vertex attributes such as position. We will see position only today, normals, UV coordinate for the textures, etc., etc. But holds any information we want to have for some vertex. This is an example. We define, in this case, an array. We are working only in 2 dimensions, so we just need an x and a y attribute for each vertex. And I defined a triangles by stating x, y of 3 vertices. At this point, I ask WebGL to reserve a portion of memory on the GPU, block of memory, in which I want to store those information. This is what this create buffer function does, and returns an handle, which is something a little bit different from a pointer, but the idea is more or less the same. an handle to that portion of memory. So if I want to use the data I put somewhere, I must use this handle. So now I have a portion of memory reserved for storing some vertex data. 3. Since we are in a state machine, at this point I have to ask WebGL, I want to operate on that buffer now, and so I bind it. It becomes the active buffer. Any subsequent call regarding buffers will happen on that one, on the one which is active, the one that I binded right now. I specify that is going to be a sort of formatting of the buffer. I specify that it is going to be an array buffer, meaning a buffer that holds an array of values, and the handles to it is stored in VBO bar. At this point, I can move the data from my client code to the server side using buffer data, which plays the values of the data array inside. Again, I specify that it's going to be an array buffer. The data are the data that I passed, and static draw is one of different ways in which I can fill those buffers. In this case, we will not see other ways. Probably I will talk about them later, but in this case I just say, okay, at the moment of creation of the buffer, I fill with the data for my triangles, and for all the program lifetime, I'm not going to change anything inside that buffer. That's why I specify static draw. There is also a dynamic draw if I want to change those values, but it can become difficult to explain you the differences now. Later on, when you see and you act on that, probably it will be easier. At this point, everything is on my GPU memory, and it's ready. I am ready for doing something. For telling WebGL how to use the data I send to it, I have to use GLSL. But since it will be covered in future lesson, for now, simply let's say that we create a program that will handle my data, the data I send to it, and use for visualizing a triangle. This GLSL program is compiled at the execution time of my program and kept over the GPU memory. There is the client side. I send the data to this program and I obtain my rendered image. We are not done yet. There are a couple of steps more. So I have my data. I send the data over the GPU. I create a program that can use those data, but the program is not indeed using them yet. I have to make a bridge. I have to make a link between the data I send on the GPU and the program that will use them. How to do that? First of all, I have to retrieve the handle, the position, the location on the GPU memory where the GLSL program expects to find its input. So, if in my program I decided that the variable that holds information about vertices is called vertex position, I can retrieve and handle to this portion of memory and store it somewhere, in this case in the variable vertex position handle. With this enable vertex attribute array, I start a communication between the portion of memory where the data are and the program, so the program can receive in input the data I want to send it. And then I have to specify how to interpret those. I have just some blob of data and I'm bridging them to a program. Before I can enable the communication, but then I have to explain how those blobs must be handled, and that's what attribute pointer, vertex attribute pointer function does. In this case, I specify that the data that are sent to vertex position handles comes in couples of 2. They are float. They don't need to be normalized because I already expressed them in a range -1, 1, -1, 1, 1. And for now, I don't have any offset or stride. We will see what they are. So I put simply 0 and 0 as the last 2 parameters. Just an explanation of the parameters of this function. At this point, I can finally draw things. So you see that the pipeline is quite complicated, and we don't even yet afford to face the problem of writing GLSL code. Basically, just as a quick recap, I have locally on my machine some object I want to draw expressed as vertex information of the object. I take all those data and I try to reserve a portion of memory on my GPU where to store them. Once I did this, I create a program that handles those data. I create the bridge between the portion of memory where the data are and my program. I send the data to the program, and at this point I ask the program, okay, now draw on the screen what I want to see. And here I specify with GL draw arrays that in this case I want a line strip. I have 3 vertices, so the first and the second are going to be connected, the second to the third. And since this is not a loop, I will see just 2 sides of my triangles. Should I use a line loop, I will see the triangles closed. 0 and 3 means that I can send, for example, a blob of much more vertices respect to those I intend to draw, and on subsequent call for any given reason, in the first call I just want to draw from the 0 to the 5th, then from the 6th to the 100, etc. This is because I can make different optimization choices when I have multiple objects. I can send multiple objects as a single blob of data. I can send different buffers, each with an object. It depends on my necessity. And the function is flexible enough to allow me to decide different ways for doing the same thing. As I told you, it can be scary, it can be complicated, but basically from drawing a simple triangles to drawing something like, let's say, Assassin's Creed's level of complexity, more or less, with OpenGL there are no such big differences. The sequence of command is this one. What changes, of course, is the logic of your client application, how it handles all its resources. But if you just focus on create the render engine, anything that allows you to render, okay, those are the commands, the basic commands that you need to know. Okay, let's try to use, I think we have time. Let's try to see something about this. So we can keep almost everything except we can delete all this part and stick with this. Nothing changes in the HTML part. Everything changes in the scripting part. Okay. So we have to make some differences here. It can become useful next lesson and on when we have more function to have some global variables. So that's why I'm putting canvas as a global. And also we need a GL instead of calling it context. We know that it is a context, but we need a GL context, so we call it GL, and we set it to null for now. Okay, so canvas remains the same function basically. But then, to be more clean coding, it's better if we put inside a try catch block the creation of the OpenGL, the WebGL context. Okay. In case of error, simply console. Then, in block, if we have an object in GL and GL is not null, we will write here the drawing code. Else, let's use an alert. Something like this. Okay. Chrome does have a WebGL context. If instead I try to open with Explorer, we don't have a WebGL context. Same thing if I use Edge. So as a workaround for this, we simply create a conditional attribution, and as a second one we put experimental WebGL, which shouldn't impact on Chrome in any way, but should provide us compatibility with Explorer, if you need to use Explorer. Okay. Another thing which is quite difficult is to debug in JavaScript can be a real pain, but to debug OpenGL can be much more worse, especially on the on the GLSL path, because you don't have any logging of error directly from your graphic adapter. But we will see how to handle such problem, basically with luck and some try. Okay, so first of all, let's create a variable. Let's call it vertices, which is going to hold the position of the vertices we want to use. Let's, for example, say express those. This is the first vertex, x and y position of the first one. The second one, let's say, is 0.5. Let's put 5. Okay. You see that this is it's just for didactical purposes that I'm putting them on onto columns and 5 rows. This is just an array, it's just a sequence of 10 floats, and that's it. But in order to understand what we are doing, I put them this way. So the first thing that we see from the slide is that I need a VBO object. And so I create it. I use the context, that this time is called GL, and I use this name to be more clear. GL.create buffer, and I allocate some place on my graphic adapter. Then I state that this one is the current in use, is going to be a GL array buffer, and its angle is VBO. Then I buffer the data. This complication here is because in JavaScript you don't have to type the variables. Of course, WebGL and OpenGL require strictly typed variables, and in this case I'm transforming the array of vars vertices in a float 32-bit array of floating points. And I intend to perform a static control. At this point, I put my data on the GPU memory. I have to create the GLSL program. In this case, I cheat and I take. Usually, such snippets of code are put on the BIP website, but today, for some reason, it wasn't working for me and I wasn't able to upload anything. But okay. In this snippet of code, we have two vars, VS and FS. Those are the two parts of a GLSL program, the vertex shader and the fragment shader. And we will see them both in details. Inside the quotes, we have the code, which looks like really C-like. We have some attributes, which are globals. We have a main, and inside the main, something happens. And we have also fragment shader, which is a second step on the rendering pipeline. Again, very similar, with the main, the specification about something that I will tell you, and the color. The first one, let's imagine something. In the vertex shader, I define the geometry of my object, and in the fragment shader, I decide everything about colors. This is just for you to know today. We will see that it's much more complicated than that, but to have a picture in mind. Then I create a program, which is just a placeholder. I create a vertex shader and a fragment shader. I compile the code of them both. I link them together, and I have created in this way the program which resides on the GPU. In program, I have an handle to this program, and that's it. For now, just keep this part. Sorry. Okay. Once I have a program, I have to set the state machine to use it. So use program straight as it's in. But now I need to create the bridge between the data and the program. So I have two. I have the handle to the program, but I need to know where the program expects I feed it my data. And so I create this variable vertex position handle. Knowing where my program is, I look for the variable position1, which is here in the code. I know that I need it for drawing, so I take its position inside this variable vertex position handle. I know where to send my data. I enable communication between program and data. And then finally, I specify how to use those vertex attributes. So, the data that are sent to this handle here comes in pairs. They are floating point, and they don't need to be normalized at all. Finally, I can call the draw call. Let's start with points. Let's say points. Starting from 0 up to 5. And let's see what happens. Okay, I miss an S. Okay, I have 5 points around in the screen. The first one is in a wrong position. Let's check what happens. It should be 0 something. There is a 0 that is not a 0. So let's return here. Where is the 0? Okay, here. Okay, the 5 points, let's say, of a house. I can change the draw call for drawing those points differently. I can keep the first one, but for example, I want to use line. If I add the lines, I see just 2 lines, because lines means that a couple of vertices for each line. I have an uneven number of vertices, so one vertex is not used, because there isn't another one that can be connected. Instead, I can use line strip, for example. If I did this, they are connected in this way. In a loop, I will see the whole thing. Of course, lines are rarely used. We will use mainly triangles. So let's see what happens if I use triangles. I have the same problems with lines. I need at least 6 vertices if I want to see 2 triangles. In this case, I have 5, so just 1 triangle can be drawn by OpenGL. If I use triangle strip, you see that we have 3 triangles. One, the roof one we have seen before, and another strange one which is on a side and partially covered by the other two, or covering the other two, we don't know because everything is red. If instead I use the loop, look, something doesn't exist. It's a triangle fan, not loop, sorry. Since one vertex is shared by all triangles on the screen, that's the result. Now I want to show you, I think we have time, how the circle thing works in this case, because it introduces one relevant problem with this kind of coordinate system that we don't have when using the standard context. At this point, we just have to change this part here. We leave an empty array and we create again the same thing we did before. Let's start with 16. Okay, let's go to 64. In this case, I have to change. 100 is no longer a valid option. We will not put it exactly in the center because 0, 0 can create problems with operations, so we simply move a little bit from the center, and then we create the same for cycle. Before vertices dot bash, I put things inside the vertex. And then the for cycle we have seen before. Use I. Okay. Instead of specifying manually each of the vertex, in this case we resorted to a procedural way for filling the array. Okay. As I explained you before, I can decide how many elements inside the buffer I want to use. In this case, since we didn't change from before, I still see just 5 elements. But of course, if I change and put the right values here, I see everything. But that's what happened. More like a Japan flag. But we don't have a circle in the middle. We have an ellipse. Why? Because there is a problem now, which is the aspect ratio. Rarely the pixels on the screen are exactly squared. It depends on the size of your monitor, which is the correct shape of your pixel. So in this case, we don't have any automatic way for correcting the aspect ratio, and we have to code this part by ourselves. It's easier than it may seem. It's just after we have created the context and we are sure we have one, we need a Y and an H. We can of course specify it hard-coded, but since there are functions able to collect those information from the environment we set up, it's clearer doing in this way. So if we change the dimension, we don't have to change everything in the code, of course. Okay. So we collect the height and the width of our canvas. We create a variable aspect ratio. Usually it is the larger dimension divided by the shortest one, and we have to use this one to correct the Y as a correction. That's it. We have to multiply the Y coordinate by this aspect ratio, and in this case, as you can see, everything returns to the correct shape. So I think that for today it's more than enough.